Right, so hope you've had a chance to get through a lot of this material. Let's just start at the beginning of the chapter. And can you see my screen, by the way?
Yes.
Okay,
Yes.
great. Great, thank you. All right. All right, so he starts off by sort of going through some of the history that inspired neural networks. They're inspired by the working of the neurons in the brain, which we don't need to learn about too much, but they have, basically a neuron has inputs and outputs, and it fires off given if its inputs are active, if its inputs have enough voltage or whatever, it fires off and triggers, and there can be chains of these things, and they can eventually compute things that that are done in your brain. I don't know a whole lot about neurons, but here's what they look like in diagram, and then here's a, so let's see, somebody needs to mute themselves. Mute, thank you. Yeah, so and this is what a cross-section of your brain looks like. This is what the neuron pathways look like in a cross-section of brain tissue. It's a drawing from some famous anatomy textbook. So you have the main part of the neuron that does all the computation is the synapse inside, and it takes inputs that are voltages from axons that come in, and then it produces an output voltage that then gets transmitted to the next neuron. That's basically all we need to know about neurons, about biological neurons. Now, so now they generalize this to logic, and so the idea is that you have inputs that are ones or zeros, and these inputs get combined in a certain way to produce an output. And so one way to produce an output is just a pass through. Whatever comes in goes out, and that's what this one is. So C is the output, A is the input. This is the AND gate. That is, both inputs are 1, then the output is 1. Otherwise, the output is 0. And this is the OR gate. That means if any of the outputs is 1, then the output is 1. Otherwise, the output is 0. And then there's the NOT gate. So this is combining an input A with the opposite of an input B. That means if B is 1, then not B is 0, and then that becomes the input. I'm not understanding why he has these double 2 arrows or 1 arrow. So, sometimes.
This is exactly the question I want to ask.
So I think that it's not important, and I looked at this. I don't think it's important to worry about that. So I think the main idea is to understand the AND gate, the OR gate, and the NOT gate, and the pass-through gate. Yeah, did somebody have an idea about what the two?
Yeah, that allows for like the OR example. It allows it to still function correctly, because the idea is you need 2 neurons connecting to C for it to itself fire. I think that's all he's trying to show.
Yeah, but why do we have 4 neurons connected? Why are there 4 things connecting to C here?
Because if A or B is activated, so you need 2 total at C connected and activated. So if B is not firing, A is firing, and there's 2 connections from A, so then C will fire. Compare that with the connection to the example to the left of it, where you have A and B. In total, they have 2 connections. So then C would fire only if A and B are connected.
Okay, so you're saying that a neuron, that this model is that a neuron will fire if it has 2 active connections.
That was my understanding. Yep.
Okay, I think that might work. I think that might work. Yeah.
What about C equals to A? What about C equals to A? If you look at the direction, it's like going, okay, yeah, it's the same. Okay.
Yeah, so that means if A is 1, then you get 2 1s and then it'll fire. And if A is 0, otherwise A is 0 and then it won't fire. So I think that works. I think Brian's Brian's understanding is the right one.
Yeah.
All right. So yeah, somebody.
Oh, sorry, just Mehul. Yeah, I agree. In the last line, just above the figure, it says a neuron is activated when at least 2 of its inputs are active.
Ah, okay, okay. So it does say that. Okay. He should have made it, it wasn't as clear as it could have been. So anyway, back to this one. So next we want to talk about the simplest implementation of a neuron, which is called the perceptron, back in 1957. And here the idea is it functions like a neuron. It has inputs that get combined in some way to produce an output. And so what you have is numbers. The inputs are numbers, which are just like the values of something. And then there are weights associated with each input. And the weights somehow, in some sense, control the strengths of the inputs. So this is a generalization of this simple model here. The inputs are combined by means of a dot product with their weights. So you take a weighted sum. X is a vector of numbers. X transpose. So X, normally vectors are column vectors. So that's why the leading term here is a transpose, because that makes it a row vector. And then you take a row vector dotted with a column vector, because if there's, normally you just consider a vector as a column vector. So X transpose W just means X1W1 plus X2W2 plus X3W3, the weighted sum, the dot product. And then so that's computed, and then it gets passed through a step function, which says that if it exceeds 1, then the output is the number itself, and otherwise the output is 0. So let's advance forward a little bit. A step function this is a really nice diagram, because this is exactly what a step function looks like. There can be other activation functions, but let me just skip forward to a couple of pages here just to show the diagram for a step function. There. So are you seeing figure 10-8 here? Does everybody see that?
Yes.
Yes.
Yeah.
Okay, thanks. So the step function is basically this one. It goes, well, now they're talking about two different kinds of step functions. The step function illustrated here is a sine function, SGN. So that means that if the input is less than 0, then the output is -1. If the input is greater than 0, the output is +1. But they also talk about the Heaviside step function, which is a step from 0 to 1. Okay, so that is, the input is less than 0, then the output is 0. If the input is greater than 0, then the output is 1. So he talks about that. He talks about different kinds of step functions, but I think the one that gets implemented in the Perceptron in sklearn, I believe, is the Heaviside step function. Okay. Okay. Yeah, so there it is. The Heaviside step function is 0 if 0 is less than 0. The input is less than 0, 1 if the input is greater than 0. And then this is the sign. I didn't need to go forward to see that. You can just see it in the equations here. Sorry about that. Okay, so he introduces a lot of acronyms here, and it's whenever you see text that's heavy with acronyms, it's good to make yourself a list, because you see all kinds of things, ANNs, you see BNN, you see TLU, LTU. The linear threshold unit is basically the step function. That's what this is. Actually, the linear threshold unit is this whole thing here, this whole system here, where you combine a weighted sum of inputs and then apply a threshold. So that's the TLU, which we'll see referred to. Okay. Next he talks about fully connected neural networks, or dense networks, where every input node is connected to every node of one level is connected to every node of the next level. And he's sort of generalizing here now. The input layer is considered to be a pass-through, so that it's considered to be a node. The input layer is sort of considered to be a node itself, and that is that that is that each input goes through a pass-through and is applied. So that's called that's considered a node. For each input, you have a node. The next thing we add here is there's a bias neuron. We've seen this before. It's always equal to 1, and it allows us to add a constant. It allows us to have models that have additive constants. So basically, that just means the output of this neuron is always 1. Okay, so then this is what a perceptron would look like in general. It's considered, it can be composed of more than 1 TLUs. Sometimes people think of a perceptron as just 1 TLU, but in fact, a perceptron is a layer of TLUs. It can have as many as you want. Okay, so this is basically the simplest diagram of a perceptron. And the output can be expressed mathematically. H and WB is the subscript, W is the weight matrix, B is the bias, applied to some input X. Given that this and this are specified, you can then specify the output. And you need this function phi, which is the activation function. And as we've seen, the activation function for the perceptron is a step function of some sort or other. But when we generalize this, we'll see we can use any activation function we want. Okay, any questions up to here?
Yeah, one question at this stage. What's the purpose of the bias term here? What does it?
As I mentioned, that allows your model to be flexible enough to include a constant. In other words, if you can make a model that says that something is a linear combination of A and B, of X and Y. You can say Z equals AX plus BY. That's a linear model, but a more flexible linear model would allow a constant to be included, right? So, AX plus BY plus C is the most general linear model.
So what's the significance of this constant adding to this perceptron?
Because when you have a constant, that means you can you're taking a linear combination of the weights. This is one of the weights. So this is one of the inputs. Sorry. So there's a weight associated with this, and that weight is the bias, is the additive constant. Does that make sense to you?
Yeah.
Okay, so so this allows you to introduce an additive constant into your model. Without it, you couldn't do that.
Mm-hmm.
You'd have to have a model that always passes through the origin, for example. All right.
Yeah, I have a question. So I want to understand what this expression means by Donald Hebb, that they say cells that fire together wire together. What does that mean?
Okay, that's the biological understanding that, so for that you really need a biologist, but that's this Hebbian learning thing. Apparently that cells that are close to each other in the brain or that fire together in the brain somehow are trained to fire at the same time. I mean, I don't know, maybe it's neurons that are near each other and get activated by the same inputs or something like that.
Hey, can I just jump in?
Yeah, a biologist. That would be good.
Yeah.
Okay, so here's kind of like the one thing we have to remember when we're doing this stuff is that this stuff is from the 1950s and the 1960s and 1970s. Okay, this is really before digital logic was a thing. Okay, so what they're running these things on, vacuum tubes. Okay, which are outputting voltages. All right, and actually the brain itself is similar. Okay, you don't necessarily get a full action potential. It can be attenuated or strengthened. Okay, and the spiking neural networks, if you want to look into that, that's more of a representation of what actually happens in the brain. But from our purposes, okay, that's why when he kind of does this appearance that he did previously, it looks like more things are going into it. Well, when you feed 0.15 volts in and 0.15 volts into the old style perceptron, you're going to get a stronger activation signal, and you get out, like something like more like 0.3 volts. It's not necessarily a binary 0-1 circumstance. Okay, so the same concept with the brain.
Yeah, that's an analog device.
Exactly.
Exactly. Yeah, and in the early days, they used vacuum tubes are also analog devices. So, but this idea of Hebbian learning, that it's not really that clear. Cells that fire together wire together. That is, the connection weight between two neurons tends to increase when they fire simultaneously. So I guess that means if something stimulates these neurons to fire together, then they learn that response. Like maybe if you see a dog and your fear reflex gets triggered, then every time you see a dog, your fear reflex gets triggered. I don't know. It seems like a tautology to me. I don't understand what.
Well, think about it this way: if you put an EEG on a person, right,
Mm-hmm.
and they'll hang out, and their EEG electrical spikes are going to be kind of mellow, right? Now come at them with a knife, all of a sudden their EEG is going to jump off the scale, right? Because you're activating all these potentials, and it's all going through. The brain works on voltage. So when you overwhelm the brain with a lot of voltage, right, through these cells that are firing together and wire together, okay, you can actually, there are also feedback loops in the brain as well. So you can actually, like, in a sense, like, kind of, maybe that's why post-traumatic stress, happens. I mean, this is not science, this is me saying this, but, if you have a gigantic stimulus which overwhelms everything, a huge voltage potential, you're going to remember that.
Well, okay, so for example, maybe as a child, you fell off a table, right, and you hurt your head. So now, tables are going to have some kind of a association with being hurt, and maybe that will go away over time. But I mean, maybe initially that's what it means, that a child who just got hurt by falling off a table, the next time they see a table, they might, some neurons in their brain might fire that have to do with expecting pain or something like that.
Or if you were attacked by a dog. Same
dog,
thing.
Yeah, that's even a better example, right? Then you'll be afraid of dogs, and then maybe in future you can train that away, but the association gets formed and has to be dealt with.
Because the weight is bigger.
Yeah, that makes sense.
I'll shut up, man.
Yeah, thank you. And I mean, not thank you for shutting up, but thank you for your biological input, because I have no knowledge of biology. Yeah, so then the neural network trains. How do you? Okay, so the idea then is you have to get these weights somehow. You don't start out with the weights. You eventually start out with, as we'll see later, you start out by randomizing the weights is the best way, but eventually you have to learn the values of the weights that allow you to get the right output, to get an output that you're trying for. So how do you do that? For perceptrons, the equation looks really simple, and it reminds you of something, right? It reminds you of, the next step for the weight is the current step plus some eta, which is the learning rate, time. It's just basically a constant that gets multiplied by the combination of the error, which is the expected output minus the output of your actual network, times the input. And this looks exactly like the stochastic, looks like gradient descent. So again, to review the terms, Wij is the connection. So I is referring to the training instance, right? J is referring to the output of the Jth neuron for that training instance. So just think that I is associated with the training instance, and J is associated with the neuron index. So here's training instances 0, 1, and 2. The bias is the 0 one, and then these are the neurons. And then as you can see, neuron is going to get weights associated with each of the inputs. So that's the W1, W2. That's W11 for IJ, W21, and W31, because the 1 means the first neuron. So
I have a
back to
basic
here.
question on this. So with the weights are updated every next iterative step. So going back to equation 10-2, the weights W matrix is not known prior to running through the network, right?
Well, you initialize it. You initialize it to random numbers, as they say later on.
Right. That was my point.
Yes, you have to start from somewhere, right? So and they made the point that if you start with zeros or ones, you won't get anywhere because the output will never change. Yeah.
Will never change.
Yeah. So back to we were looking at the description of this equation. So this is the update equation, and we were just kind of looking at the description of it to make sure we understand what every term means. So I is referring to the training instance. J is referring to the neuron. So I think I spoke wrong before. IJ. So it would be W11, W12, and W13 would be these three. Would be the three weights that come into this first TLU. Does that make sense? And then so J refers to the first TLU here. And then Yj minus Yj hat, that means the known value of the output minus the predicted value of the output. And the predicted value would be at first nonsense because you'd be using the random weights to predict it, right? So it wouldn't mean anything, but it wouldn't be very good. It wouldn't be expected to be very good. And so the difference might be large, and that would lead to a larger update. So yeah, so that's the update equation. And then he talks about applying it to the iris data set, which he does in, let's see if I can get rid of this. And then I can go to the iris data set. Okay, so this is in the notebook. He basically just imports the data set, the iris data set. He imports Perceptron from scikit-learn, which has a Perceptron in it, and makes a prediction, and then plots the decision boundary with different inputs. So the Perceptron found this linear decision boundary, and that's basically what it was designed to be able to do, to find linear separation, linear decision boundaries. And as he mentions, there's infinitely many of them for this problem. The Perceptron doesn't necessarily find a unique solution. The next thing is what we look at the different activation functions. I think many of you have seen these. The sigmoid function is an S-shaped function that goes from -1 at negative infinity to 1 at positive infinity. Sorry, it goes from the output goes from 0 at negative infinity up to 1 at positive infinity. It's an S-shaped function, which you can see here. Let's see, the sigmoid is this one, is the green one, right? And then we also have a variant of it, another S-shaped function called a Tange function, which it's symmetric. The output is -1 for the output tends towards -1 as the input goes towards negative infinity, and it tends towards +1 as the input tends towards positive infinity. So these are all the various kinds of inputs, and you can see that these are sort of more sophisticated. For example, the Tange function is essentially a more sophisticated version of the sign of the SGN function, which is that SGN step function. Okay.
Joseph?
Yeah.
I have a quick question. Do you know if we're going to cover the theoretical justifications for picking one activation function over another at some point?
I don't think we are. I think this is very much an art that people choose activation functions that work for them and in their problems. And I think that this one here, the the ReLU function is sort of a general purpose one that works for most problems. There are all kinds of papers about variations on ReLU. So there's, you know, there's just all kinds of them. There's, I remember in FastAI, he introduced us to a number of them. One of them is when you have, instead of 0 at on the negative side, you have a small increasing function here. So that you don't get this sharp corner, this is the problem with the ReLU function, is that it has this sharp discontinuity here and the derivative is discontinuous. Whereas if you make this a little smoother, then you don't have that problem. There's one function that just gives you, that just has a pre-shaped function here, so that there's no extra parameters to learn. And then there's another variant that has a parameter that controls what this little rise looks like. So yeah, there's a lot of parameters. There's a lot of variants on this ReLU, but we won't really look at any of the theoretical justifications. The one thing to remember is that ReLUs are good for internal layers, but then when you go to the output layer, you often want a sigmoid or a Tange to help you put the numbers in the right range. For example, if your outputs have to be positive, then it makes sense to use a sigmoid function, and it makes more sense when your outputs have to be probabilities. That's the ideal case for the sigmoid function. It makes the output, it squeezes the output to be between 0 and 1. But if your output is bounded and not bound, if it's not a probability, so it's not bounded by 1, but it's bounded by some other number, then you can just have a scaled sigmoid function and that will cover it. If your function is allows negative values and has a boundary and has bounds that include negative, that's bounded on the left side and bounded on the right side, then the Tange function is good. Anybody have any experience with particular activation functions that they liked better or that worked better for them, and they can say something about it?
Or perhaps you constructed your own activation function.
Yeah, you can do that too, actually. You can play with
some who have, I just don't understand enough to be able to do the same.
I'm sorry?
I don't understand activation functions well enough to be able to make my own.
Oh, to make your own, yeah.
I don't think that necessarily you need to like stress out about the activation functions. It's really a case of, first of all, you have your default one that you use, and that's most of the time for most people it's ReLU, right? So then you get a working model and you're trying to tweak the model to be better, okay? And then at that point you start doing some other stuff. And I would probably, I like to try CeLU. That's why I posted it for everybody. I think in the past, TANH has also been useful, particularly as a replacement for sigmoid at the output layer. Softmax is also around in there as well. He goes into it a little bit. There are different types of problems that are used traditionally for different ways. And, it comes down to just trying what works. So it's just like, okay, I got something good now and let me try something a little bit different.
I think the way to look at these activation functions is a hyperparameter. Once you got a working model and you think you need some more, you need something, maybe it doesn't perform as well as you wanted to, you might try some different kinds of activation functions, and they're easily look upable on the web. There's lots of Medium tutorials about this or that activation function and why it's good. The main thing to remember is that the ReLU activation function has dominated the literature now, and the reason is that it's very quick to compute. It's extremely fast to compute. It's just one line, and these are much more compute intensive. A hyperbolic tangent function or a sigmoid function are much more intensive. And so the ReLU function, one, because it works, it introduces a nonlinearity. That's all you need the activation function to do, is to introduce some kind of a nonlinearity. Even this even this sine function, or the Heaviside step function, which he also talks about, that would be this function. They introduce nonlinearities, and that means that when you stack perceptrons on top of each other, it allows you to solve any kind of problem actually, given that you have a nonlinearity.
I would just say
So,
I've never, ever used the step function. Maybe there is a place for
no,
it.
no, that's just for the people who
it's just,
introduced the
it's just,
perceptron.
yeah, I'm just saying, you
Right.
know, on a binary data set, you know, when you're outputting, you know, ones or zeros, I probably, you know, would avoid it. That's why we use the ReLU. That's why I use the.
Yeah, I mean, but before they thought of it, I mean, we have to go back in history, and people didn't think of the ReLU until relatively very recently. And the first perceptrons were built with these sign functions, and actually the first ones were with the sign function and the Heaviside function. So yeah, so this is just a historical exercise to look at the different these different activation functions. And then we realize that most of the modern neural networks are using ReLU as the go-to because of its speed. Let's see.
I think that TAN is still used in recursive neural networks, in LSTM and stuff like that.
Oh yeah, right. Yeah, I mean, yeah, Tange and Sigmoid are also used. You're right in LSTMs. For reasons that they help to constrain the input, they help to constrain the outputs if you need to constrain them. So, you know, we're not only going to be using ReLUs, we still have to use sigmoids and tanges, right? But we're probably, as Stephen said, we're probably never going to need to use step functions, or rarely. Anyway, thanks for that. Back to the text. Let's see. So he goes through this exercise with the iris data set. Let's see, somebody needs to mute themselves. Okay, I think it's done. Okay, so then he goes through this problem where the Xor problem, that is an exclusive OR, which is a logical gate that says the output is the input. There's two inputs, and each input can be 0 or 1. The output is the OR function, except when the two inputs are equal, and then the output is 0. So it's kind of like the same as the OR function, except the mapping of 1, 1 is 0, whereas 1 or 1 would give you a 1 in logic, but 1 XOR 1 gives you 0. It's just the definition. So if you look at the table, and you can define it by a table, right? A table of inputs, and there's 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1, right? And so 0, 0 gets mapped to 0, 0, 1 gets mapped to 1, 1, 0 gets mapped to 1, and 1, 1 gets mapped to 0. That defines the exclusive OR function. Now he has a drawing here. The two axes are the two inputs, and you can see the problem that this poses. There's no linear boundary that cleanly separates the two classes, right? The green square class and the triangle class, right? You can't draw a linear boundary that separates these. And I guess they realized that a single perceptron can't solve that problem, and that set them back for a while until they realized that by putting multiple perceptrons together, stacking them, you can solve the problem. And he does that here. You can follow this. I did this just for the first case, 1, 1. When both inputs are 1, you can demonstrate for yourself that the output is 0. And you can try it for the other combinations as well. Okay, so now he talks about multi-layer perceptrons. And all that is a stack of perceptrons. So in other words, an ordinary perceptron has an input layer and an output layer. That's all. A multi-layer perceptron has a hidden layer and maybe even more than one hidden layer. In this case, they're just showing one hidden layer. Okay, so this is the simplest multi-layer perceptron with just a hidden layer. And notice that the inputs are fully connected to the hidden layer. That means every input is connected to every node, or TLU, in the hidden layer. And on the next level, every node in the output layer is also connected to every TLU in the, or node in the hidden layer. So does that make sense as a structure? And remember that we're always adding an extra node for the bias. That makes our model totally flexible to have constants. Okay, let me look at questions. Somebody had a question. When ReLU evaluates to 0, won't that unit behave simply as linear? No, because the input, well, the input to that unit might have been -10, and the output is 0. But if the input is -5, the output's also going to be 0. And if the input is +5, the output is going to be +5. So that's not a linear function. I mean, if you look at the ReLU function, yeah, sure, it's linear in pieces, but the whole function itself is not a linear function. So let's go back and look at that, forward I mean, and look at that ReLU function again. Okay, so let's see. It's a little confusing because the scales aren't the same on the x-axis and the y-axis. But this purple dotted, double dotted line, this is the ReLU function, and you can see that it's not a linear function. It's nonlinear, and especially you'll see that if you have the approximations that people use where they have this smooth little corner here, that's clearly a nonlinear function. Okay, a linear function would just be a line in the whole plane, if that makes sense. So did that answer your question? We can speak up. Okay, that's all right. Okay, so so he introduces this multi-layer perceptron, and then he shows how you can. Oh, then he talks about backpropagation, which we've discussed this. We're not going to discuss this in detail, but I'm thinking about going through. There's a really nice appendix on auto differentiation, and I think that would be nice to go through that as part of this chapter. So we might be able to have time to go through that in the future as we go through this chapter. But right now, let's just think of backpropagation as using the chain rule to get from the output layer back to the input layer, and calculating the adjustments to the weights. We've already talked a little bit about this when we talked about gradient descent. So we don't need to, unless people have specific questions about it, we don't need to review that part. You can if you get confused in this section, you can go back to the discussion of gradient descent back in chapter 4. So this is the key point. In 1986, the paper by Rumelhart and Jeffrey Hinton and Ronald Williams showed how to do backpropagation, came up with this backpropagation algorithm that allows you to do this automatic training of neural networks. And it's basically the gradient descent algorithm that we already used. So if we remember how that works, we use 2 passes. We go forward. The forward pass is actually starting with the inputs and applying the weights to get every one of the outputs. That's the forward pass. And then the next thing you do is you compare those outputs. You can put those outputs then through a loss function that compares them with the expected values of the outputs and calculates a derivative. So it basically tells you the sensitivity of these of the outputs to your input parameters. And then those derivatives allow you to compute a correction that you can then apply to the the weights to get you closer to the desired outputs. So the training process always starts with this is always for supervised. This is always a supervised process. We have the answers. And we try to predict them with our network. We compare them with the correct answers, and then we take a derivative of that of a loss function. The loss function computes some kind of the loss function basically is a function of the desired outputs and the outputs that we predicted, and if we take the derivative of that loss function, that tells us how we should adjust the weights of the hidden layer to get us closer to the outputs that we want. And doing this automatically is called auto differentiation, and that's there's an appendix that we might want to look at later on in our journey through this chapter. So this is the algorithm. This is the training algorithm. It's basically in words. So you start with a mini batch, and the default is 32 examples for the mini batch. You pass each example from the mini batch through the network's input layer, and remember that's a pass-through that sends those numbers directly to the first hidden layer. The algorithm then computes the output of all the neurons in this layer for every instance for all 32 instances in the mini batch. And we know how that's done. That's from applying the function that we talked about, the activation function applied to, let me go back so you can see just to connect this to something you know. Just this schematic tells us what's going on inside of each node. We're taking this sum, which is a weighted sum of the inputs. That's the dot product of the weights vector with the input vector. That's what this sum is. And then we're passing that sum through an activation function, which gives us an output. And that output can be, if it's a ReLU, the output can be either 0 or some positive number. Okay, so that's the first step. So that's the forward pass. You pass it through, if you have more than one layer, you pass it through all the layers until you get to the output, and that's called the forward pass. Then you measure the output error using some kind of a loss function that compares the predicted output with the known output, with the true output, what we expect the true output should be, and it's some measure of the error. That's what a loss function does for you. By differentiating the loss function, we hope to get to a point where we hope to adjust it so that we're getting to the point where the derivative is 0, so that no further adjustment is needed. And so every time you do the forward pass, then you do the back propagation by applying the chain rule, and the goal of that is to compute a correction that you then apply to the weights. So that's what's going on here with the loss function. The chain rule is always differentiating the loss function with respect to weights. And at the end of that, you get a correction. That's this last step here. And then here's where he mentions about the fact that you always have to start somewhere you have to start your weights from somewhere. And it's a bad idea to start them with all 0s or all 1s or all 5s or whatever. It's the idea is that you have to randomly initialize the weights in some way. Okay, and then he talks about okay, this original paper in 1986, they replaced the step function, which was what people were living with up until then, replaced it with the sigmoid function. So that was the first iteration of the development of these activation functions. And I guess the the good thing about this is that it's an analog function, as Stephen pointed out. It's closer to the way the brain operates. Let's see. And also the other advantage of this over the step function is it has a derivative everywhere and allows the gradient descent to make progress at every step. So he mentions that the backpropagation algorithm works well with many other activation functions. This was the question that Brian raised. There are lots of activation functions, and talks about the hyperbolic tangent function, which can be computed in terms of the sigmoid function. So this is the sigmoid function. It's just 1 over 1 plus e to the minus z. And remember what z is. It's the weighted sum. It's the dot product of the weights with the inputs. All right. So, and then it gets to the ReLU function, which is computed in a single line, and it's the quickest one, and that's why people use it. Okay, so now there's two more sections in this chapter. Two more sections I want to get through today. How do you apply regression? How do you apply multi-layer perceptrons to regression problems, and how do you apply it to classification problems? So he points out regression, there's lots of interesting, well, in machine learning, supervised machine learning, there are two kinds of tasks. One is where you're trying to classify things, put them into label them with a series of classes, or maybe more than one class. You might want to label you might label, well, there are cases where things can have more than one label. So for example, if you look in a cloud, there are more than one, if you look at a sort of a photograph of the sky that contains clouds, and then you ask for what kind of clouds are in the photograph, there's not just one label, there could be more than one kinds of clouds. And so, you might have like 10 categories of clouds, and you might want to label the photograph with what kind of clouds are found in that scene. And you could either give a single label for all those clouds, or you could give a probability, sorry, a single layer for all those clouds, a single label for each cloud type, 1 or 0. In other words, it has cumulus clouds, that would be a 1 for cumulus clouds. It doesn't have cirrus clouds, so that would be 0 for cirrus clouds. So it could have discrete labels, or it could have continuous labels, which would be like, I think, there's 99% probability that it has a cumulus cloud because I was able to recognize a cumulus cloud through my network. So the labels might be soft labels, or they might be hard labels. And then the other kind of task is a regression task where you're actually trying to compute a continuous number. So that's the two different kinds of tasks. So for example, real estate prices, you're looking at the characteristics of a house, the square footage, the location, the number of bedrooms, the number of bathrooms, and then you're trying to put all of those things together, all of those inputs together, and predict what the price is, and the price is a continuous number. So that's a regression problem. So he talks about what the network architecture would look like for a typical, if you wanted to use multi-layer perceptron. And so, one input neuron per feature. So for example, if you're looking at the MNIST data set, that would be the pixels, 784 pixels. Hidden layers, depends on the problem, but at least one for a multi-layer perceptron. It has to have at least one hidden layer, 1 to 5. Maybe that's only limited by your laptop computing power. Neurons per hidden layer depends on the problem. You can have what they call a narrow network with only 10 neurons, or a wide network with 100. Output neurons in a simple problem, it's just, you're just predicting, like for example, if it's the housing prices problem, it's just one, you just need one output. But in other problems, you need an output vector. So you need one per prediction dimension. The hidden activations, this is what we were talking about before. The hidden activations are usually ReLUs, or SELUs. I guess Stephen has put up an example of an SELU. They could have none. They could just be linear layers, or they could be ReLU. Let's see. Oh, I'm sorry. This is the this line refers to input. Output activation could be none, or ReLU, or logistic, or Tange if you need bounded outputs. So the output activate the hidden activations are always going to be usually going to be the same. They're always going to be usually going to be ReLUs. The output activation, you might just accept the output of the hidden activate of the last hidden layer as is, or you might use a ReLU, or you might use a softmax, or you might use a logistic function, or a Tange function if Tange, T-A-N-H, is a hyperbolic tangent function if the outputs are bounded. So the output activation, sometimes you need to think about what you want. You need to think about the problem, and that will help you decide what the output activation function should be. If you want a probability, then you might want a sigmoid function on each of the outputs, because that gives you something between 0 and 1. And then you also have to select the loss function. If you're dealing with a output with a continuous output, the loss function we've seen before is one that's often used, which is mean squared error. But we've also dealt with cases when you have a long tail, when you have a distribution that isn't necessarily, the inputs aren't distributed in a Gaussian, a bell-shaped curve, but they have a long tail. And in that case, outliers could be a problem. So instead of using mean squared error, you might want to use mean absolute error. And then he talks about this third loss function that you could use, which is the Huber function, which basically is a combination of both of these. It uses the mean squared error for small values, for small differences, and mean absolute error for large differences. And that prevents it from being dominated by the outliers. Remember, that's the problem with mean squared error, is it because everything is squared, the differences are squared. If you have an outlier that is a prediction that is way different than it should be, then that's going to add a large term to the sum for mean squared error, and that term could dominate the whole thing. And in some cases, that's bad. You don't want to have it dominated by one data point. So then you would use the mean absolute error instead, or the Huber function, which may be even better. Okay, so that's regression MLPs, and then we will do examples of this in TensorFlow in the next meeting on Wednesday. Classification, it can also be used for classification, and here the network architecture is a little different. You have a hidden layer, and then the output layer is for example, could be a softmax that if you want to, if you have several different classes, the output could be several different classes, then you might not want just a hard classification. Normally you could, not normally, but you could just say the output, so these outputs, the output layer would be associated with, say you had a problem with 3 output classes. That's how you would define the architecture. The architecture of the output layer would be, there would be 3 neurons on the output layer, 1 for each class. And the way one could do it is you could say, all right, whichever one is maximum, whichever one of these has the highest value, that's the class that I'm going to apply, that I'm going to predict. But a more sophisticated way would be to look at to not do that yet and just look at the probabilities. So take each output, and we've seen this when we learned about the softmax function. You take each of these outputs into a softmax function, and the output of that softmax function would be, so that would be the activation function on top of all of these output layers. And the output of the softmax function is something between 0 and 1. And the outputs have to add up to 1. If it's a multi-label binary classification, that means that you can only have one label, okay? And so that way the softmax the outputs of the softmax have to add up to 1. So, you know, you could say, you could try to predict colors, red, green, or blue, and one output could be, you know, 90% red, 5% green, and 5% blue is my prediction. And then later on, you can say, I want to make that a hard prediction, so you just take the largest one and make that your prediction. But for a lot of purposes, you may not want to do that right away. You might want to keep the probabilities. And then the third class of classification problem is the one I talked about before, where you can have several labels, just like the multi-label binary classification problem, but each example can be labeled with more than one different class. So it can be each thing can have 2 labels on it. This could be for like in an automatic driving. A lot of applications are driven by that. You look at a scene, and you can label the scene. Does it contain other vehicles? And then so there could be a bus, there could be a train, there could be a car. So each scene could have many different labels. Okay, but that can also be handled by the multi-layer perceptron. Okay, now he says, we don't have time to do this, but so I think this is what we'll start with next time. He says, do problem 1 at the back of the book, and let's just, at the back of the chapter, let's just look at that really quickly, because this is a really great exercise to do. See, I think I skipped too far, didn't I? Let's see, no, still in the right chapter. Yeah, this is the last part of fine tuning. Exercises, I just went forward. The first exercise is go to this TensorFlow Playground, and we can just quickly look at that, see what it looks like. Why can't it do that? Yeah. So you can see this is an active simulation. You can build networks with as many hidden layers as you want. You can start with just one hidden layer and build up from there. But it's really great. I mean, you can give it inputs. You can give it as many inputs as you want. You can put as many neurons in it as you want, and then look at the outputs. And you can press buttons and train it. You can determine the ratio of your training set to your validation set. Let's see, you can add noise. You can add noise to your data points. You can control the batch size. And you can see the effect of all these things on the output. And the loss function. And remember, you're trying to minimize the loss function. So you can see what happens if you add or take away neurons. I forget how, you can take away. You could take away, now you can have just 3 neurons instead of 4. See if that does any better. And it seems to do a little better. There's a lot of things you can play with here and just get a feeling for what neural networks do. And this is something that that Google, that TensorFlow that was created by Google did to help people to learn about neural networks. So I would recommend that everybody does that. And he basically goes through this. It's a long exercise with many different small pieces, but so I don't think it'll take a long time to do. It's just that you have to read through what each piece is and try to do what. So he says, okay, trying different activation functions, trying ReLUs or Tanges. There might even be a way to put a customized one in there for Brian, because you were asking about that. See if, okay, modify to have just one hidden layer with 3 neurons, train it multiple times, reset the network weights, click the reset button. That basically just generates new set of random weights. And you can see how it gets stuck in a local minimum. So if you start with the wrong set of random weights, you might get stuck in a local minimum. And that's why, I guess in the I guess in the previous chapter 9, we looked at doing iterations. So you start with, so in any problem where you have random initializations, you always want to do it more than once to make sure that you're actually converging to something that's not just a fluke, that's not just a local minimum. So if you do it like, 10 times and it always hits the same result, then you know you're doing, you have a sort of a robust result. But if you do it 10 times and 3 times it hits one local minimum and 3 times it hits another one, then you know that you're not, and the other 4 times it hits a third one, then you know that this isn't a robust solution. So it's always good to repeat the solution and make sure that you're converging to the same solution. Explore what happens when networks are too small. Remove one neuron to just keep two. So this isn't it doesn't take a long time to go through this, but and then if you're like me, you're going to want to play with it. This is probably the most important part. Now that you did all the suggestions, all of the author's suggestions, you should just play with it, come up with your own suggestions to do this. What if I double the number of layers, or change the input in some way, or change the number of outputs, and see what happens. Change the initialization, change the optimizer. There's a lot of things you can play with and just see what the effect is on the output. Change the batch size, change the normalization technique. So this is a really fun thing, and I think that everybody should definitely do this before we start next time on Wednesday. It won't take you that long. At least up to step 7 if you don't have time to do your own exploration. Okay, so with that I'll end because I've gone over by 2 minutes already. But let me just make sure let's see if we have any questions. Somebody asked about, I guess Yuri says, what are good techniques for removing outliers? Yeah, I guess in chapter 9 they had some techniques for anomaly detection, and he actually gave a number of different techniques that you might try, Yuri. GMMs is one, Gaussian mixtures, but he also talked about just using PCA as one way to do it. So I think that if you look in chapter 9, he's actually mentioned a number of different ways to do anomaly detection, and that's the same as outlier detection. That's one thing about this book that I like. It's got a lot of material in it, and sometimes too much to absorb all at once, but it's a reference. It's actually a reference book. So when you come across a problem and you need to do anomaly detection, you remember, yeah, we covered that in chapter 9. I don't remember exactly what we did, but all the techniques, he actually discussed a number of techniques, and I can go back in there and look at which one, try them and see which one is best for me. I can also look online and see if there are any new ones that got discovered after 2019. Isolation forests. Yeah, that's another technique that he mentioned. Brian mentions isolation forests. By the way, you don't have to just comment on the chat. You can speak up. But yeah, isolation forest is one. Yeah.
I'm not 100% sure that isolation forest will apply to the situation, but it's something that I've been curious about using for anomaly detection.
Yeah, I guess the isolation forest is where you, maybe that's the one where you just randomly you do all the splits and all the trees. You grow them randomly instead of by selecting thresholds at random, right? That's the definition of the isolation forest. We can go back to let's look at it really quickly.
Yeah, thanks. I definitely will look into it. And with GMM, it looked like it's you have to do something to a time series, like do like a fast Fourier transform first. So that's why I didn't see any easy way to immediately do Gaussian mixture models.
So you have a time series? That's your input?
So it's like a very small problem, but basically there's a technique that works, but it's not sensitive to outliers, but it cannot be changed by like postulation of the problem. So I need like a quick way of like just catching outliers and removing them, and it doesn't have to be real time. It can be post processing. So
I see. But is this is your data a time series? Is that?
Yeah.
I see. Oh, yeah. Fourier transform might not work well because an outlier can just make the whole thing crazy. Like if you have a sudden spike in a time series, then that will trigger all kinds of modes, all kinds of frequencies, and it'll really mess up your Fourier transform.
My experience with Fourier transform is unless it's a cyclically repeating function, don't waste your time.
No, I mean that's too general. I think. I mean, Fourier transform is a really powerful.
I'm a general. I mean, it's a powerful tool, but especially for market data, we tried to apply Fourier transforms to market data a long time ago. Total waste of time.
It is actually market data. So.
Oh, okay.
Yeah, don't waste your time with it. Do something else.
Okay.
Anyway,
yeah, I'll look into isolation forest. I haven't heard of this before. And
well, if you sorry, go ahead.
I think I missed part of chapter 9.
Yeah, I think he lists a bunch of different anomaly detection techniques that would be worth your while to look at. But I just wanted to say that it sounds like an interesting problem you're dealing with, and if you do come up with or even if you don't solve it completely, if you come up with something, it'd be interesting to, to post it on our Slack channel and people can discuss it.
Yeah, I mean, if
sure.
if you're just trying to do it for stock prices, I wouldn't mind working a little bit. Right? I have that same problem.
Sure. Yeah, maybe I'll formulate the problem better and post it.
Fair enough.
That'd be great. Thank you. All right, everyone. I'll sign off. I'm sorry I went over, and we'll meet again on Wednesday.